So let's talk about analytic complex functions. And to start off, let's actually just define what a complex function looks like. So a complex function is going to be some function of z, where z is a complex variable. Remember, z is equal to x plus iy, so it's got a real and an imaginary component. And the complex function will also have a real and imaginary component that depend on z. So we'll have the real component that is a function of z, and we'll have an imaginary component, f sub I, that is also a function of z. So this r here stands for real, and this I here for imaginary component. So we've got two components of this function, of this complex function, and each of those components are a function of the complex variable z that has two components, a real and an imaginary component as well. Okay, so now the definition of an analytic complex function is that this function f of z is analytic if f of z, if that function, if f of z is uniquely differentiable at every point in z in some domain. Okay, so I'll just say within the domain. So we might think of that as so here's our domain. We've got some real and imaginary, and remember z is just at some point in there, and so we can look at some domain in the complex plane, or some domain of z, and at every point in that domain, if the function is differentiable, uniquely differentiable, at every point in that domain, then it's said that function is analytic within that domain. So let's look at we've got to be able to differentiate then this complex function. So let's look at the definition of the derivative of some function. So derivative of a complex function. Okay, so the derivative of that function with respect to z, and we'll also call this f prime of z, is the same as the derivative of any function that you're used to. What we're going to do is take the limit as delta z goes to 0, and we say that the derivative is f of z plus delta z minus f of z. So my change in that function divided by the size of that change, or delta z. So this is the exact same way we define a derivative for an f of x, for example, and we would say that we'd look at a small deviation in x and look at how much the function changes divided by the deviation that we looked at, or the delta x. Well, we're doing the same thing here, except we're looking at complex variables, and so we have some deviation delta z from our current location z, and we're going to look at how the function changes. So this is a delta in that function divided by that delta z. We're going to look at that as in the limit as delta e, or delta z, goes to 0. Okay, so we can actually just rewrite this as the limit as delta z goes to 0 of delta f over delta z, where this here is delta f. And And we can also divide this into its real and imaginary parts. So again, as delta z goes to 0, of delta f real plus I delta f imaginary over, and I can, so I've divided that function up into real and imaginary parts, and I can do the same with the z. I can divide that up into its real and imaginary parts, so that would be a delta x plus I delta y. Okay, so these all, each of these are just a different way of expressing that derivative. And I'm not going to work through, we can manipulate this equation a bit and use some different definitions here. We can actually turn it into, in terms of r and theta. So where delta r is defined as delta x squared plus delta y squared. We could define a delta theta, and that is the arctangent of delta y over delta x. We can define that delta x is related to r and theta by delta r times cosine of delta theta, and delta y is delta r sine delta theta. And then finally, we could apply this relationship here, that e to the minus I delta theta is equal to cosine of delta theta minus I sine of delta theta. Okay, so we can plug these relationships here into that equation there, and write f prime of z as this function here. So we can say that it's actually equal to the partial of the real part of the function with respect to x times cosine squared of delta theta plus the partial of the imaginary with respect to y times sine squared of delta theta plus the partial of the real with respect to y plus the partial of the imaginary with respect to x times sine delta theta cosine delta theta. That's the real component of this of the derivative, and then the imaginary component is the partial of the imaginary portion of the function with respect to x times cosine squared delta theta. That should be a minus the partial of the real with respect to y times sine squared of delta theta plus the partial of the imaginary with respect to y minus the partial of the real with respect to x times sine delta theta cosine delta theta. Okay, so we can write this derivative this way. And at this point, we want to introduce what are called the Cauchy-Riemann conditions. Cauchy-Riemann conditions. All right. So you can show that if a function is analytic, it obeys the Cauchy-Riemann conditions, which are that the partial of the real with respect to x is equal to the partial of the imaginary with respect to y, and that the partial of the real with respect to y is equal to the negative of the partial of the imaginary with respect to x. Okay, so these are called the Cauchy-Riemann conditions. So if we plug these conditions now into this f prime equation, we find that f prime of z can be written as, and I'll just start off here, so we've got df, the real with respect to x plus the imaginary with respect to y. Well, the real with respect to x is equal to the imaginary with respect to y. So I'm going to just put it in terms of the real with respect to x. So we'll get a dfr dx times a cosine squared delta theta plus sine squared delta theta. Okay, so that's that first term there. And then the partial of the real with respect to y is equal to the negative of the partial of the imaginary with respect to x. So if I just plug that right into here, then we've got a negative and a positive of the same term, and so this whole term will drop out. Okay, so then we can go on to the imaginary portion of this, and we'll say, let's see, df I dx right here is equivalent to df, or the negative of dfr dy. So let's put it in terms of df I dx here. So we'll have the imaginary with respect to x times a cosine squared of delta theta. And then when we plug in, instead of dfr dy, I'm going to plug in a negative df I dx right into there. That becomes a positive, and then we've got that sine squared. So plus sine squared of delta theta. Okay, what you can see now, oh, and then the second term again disappears because the partial of the imaginary with respect to y is equal to the partial of the real with respect to x. So if we just plug that right into there, those two terms cancel, and so that all cancels out. So you can see that the Cauchy-Riemann conditions make it so that this derivative is independent of theta. All of these thetas drop out because even these guys are going to disappear because cosine squared plus sine squared is equal to 1. Okay, so we can write this as the partial of the real with respect to x plus I, the partial of the imaginary with respect to x. And from the Cauchy-Riemann conditions, we can actually rewrite this function. Instead of in partials with respect to x, we can write them in terms of partials with respect to y. So that's equal to, instead of putting in dfr dx, we'll put in df I dy. So we get the partial of the imaginary with respect to y, and then plus I times df I dx, which is equal to negative dfr dy. So I'm going to put in dfr dy, and we'll change this guy back to a negative right there. Okay, so this is f prime of z. So if this function, if f of z is analytic, that means that it obeys the Cauchy-Riemann conditions, and the derivative of that function can be written as we've written and boxed here at the end. So this is the derivative of an analytic function, or an analytic complex function. Okay. Okay. So let's take this one step further now and look at our complex velocity potential that we developed previously. So the complex velocity potential, remember we defined that as capital Phi is equal to little phi plus I psi. Remember, the little phi is our velocity potential, and this little psi is a stream function. Okay, so let's apply. Let's look at the derivative of this function. So the derivative of phi with respect to z, if this is truly an analytic function, then we can use these relationships here to look at this derivative. And so we'll say that that is equal to, let's look at this first term up here. So it's the derivative of the real with respect to x plus I times the imaginary with respect to x. So it'd be equal to d phi dx plus I d psi dx. Okay, so that's one way to write it. And then if we look at with respect to derivatives in y, then we would get the derivative of the imaginary with respect to y minus I times the derivative of phi, which is the real part, with respect to y. Okay, so we might notice now that this is the definition of our x velocity. Both of these guys, actually. Both of those guys are the definition of our x velocity from this velocity potential, or from the stream function. And we might notice that these two guys are related to Vy. Actually, it's the negative. Once you include that negative sign out front, it's equal to negative Vy. So that means that we can write that the derivative of this with respect to z is, we can write that as Vx minus I Vy. So the derivative of our complex velocity potential will tell us what the real portion of that just tells us the x velocity, and the imaginary portion of that tells us the negative of the y velocity. So we're going to actually call this this function of w. So we'll just call this w of z. W of z is the derivative of capital Phi with respect to z, and we'll call this the complex velocity. Because its real part tells us the x velocity, and the imaginary part tells us the negative of the y velocity. Now notice that it's actually the complex conjugate. Wz is actually the complex conjugate of the velocity in the real and imaginary planes. Okay. In the real imaginary plane. Okay, and we see that that phi does satisfy, phi satisfies the Cauchy-Riemann condition and is an analytic function. An analytic complex function. And the way we know that it satisfies the Cauchy-Riemann condition is because of these right here. So because we know that the velocity in the x direction can be written either way, d phi dx or d psi dy. Both of those are expressions for velocity from this complex velocity potential. And so because those two are equal, they satisfy the Cauchy-Riemann condition, which says, if we come back up here, that the derivative of the real with respect to x is equal to the derivative of the imaginary with respect to y, which is exactly what we see here. We've got the derivative of the real with respect to x, the derivative of the imaginary with respect to y. Those two we know are equal. And so, so that satisfies that first condition. And then the second condition here, we know that the velocity in the y direction can be written this way. And that is the derivative of the real with respect to y, right there, d phi dy, is equal to the negative of the derivative of the imaginary with respect to x, which is this term up there. We've got this minus sign outside there, and so so again, this satisfies this condition here. So that's how we know that this complex velocity potential satisfies the Cauchy-Riemann condition, and is an analytic complex function.